Okay, so what I'm hoping to happen today, after all these technical difficulties, is that I'm gonna spend like I don't know, 20 minutes or so to explaining you three-dimensional multibody dynamics. And like promised earlier, this will be explanation that we only look at the differences between the two-dimensional planar and three-dimensional spatial. Okay, the camera is frozen. So one more thing. All right. Let me see, how is my camera? Oh yeah, it's frozen. So let me do this. And then this. And I'm back. Well, you see what happened. I just, obviously I touched that PowerPoint presentation, and whenever I'm touching the PowerPoint presentation, it's doing this annoying thing for me. So it's resizing the presentation, and that's that's not good. So final settings I need to do is this. Ah, come on. Not my day today. Now I'm gonna lock it. I'm not gonna touch the size anymore. So that was the last final thing. All right, so just checking that it goes well eventually because of this delay. Seems to be okay. Seems to be okay. Let's just kind of scroll a little bit left. Yep, now it's good. All right, so I'm gonna spend, I promise you, 25 minutes, 20 minutes. Well, let's say 25 minutes max, explaining about what is the difference between the planar and spatial multibody dynamics. And we are not going to redo the whole story. Remember in fall, I explained everything about getting started with the concept of virtual work and explaining how you can map the global coordinates to generalized coordinates, and how you can make that happen with help of virtual displacement. And in virtual displacement, you have this partial operation and all that kind of stuff. We are not going to look in details. We're going to simply, kind of focusing on what is it, what makes three-dimensional description to be a little bit challenged, and that's about it. And then really what I would like to do today is that I would like to jump to my favorite topic, the topic that I like a lot, and that's a flexible multibody dynamics. This time, the flexible multibody dynamics, we really wanted to look at the most often used methods, or maybe the most often used method, which is called the floating frame reference formulation. Floating frame reference formulation is a method that is used pretty much in all the commercial software, and it allows you to describe the flexibility of all different shape and kind of bodies within the multibody framework. So what that is about, that's going to be pretty much my presentation today. Now, with that, let's first summarize what we discussed last week, and I'm going to move this a little bit left, so if there's any comments, I can see your comments. All right, so last week we discussed about Rodriguez equation, and Rodriguez equation is, put it in short, it is like a mother of all the methods that are using four parameters. And remember, again, the important thing about four parameters is the fact that these four parameters are not completely independent, but the four parameters are coupled one way or another. And they're coupled in a way that there's a one constraint equation that limits the possibilities how these four parameters can change their numerical values. There is a one constraint equation, meaning that initially you have four parameters, but because of the one constraint equation, the one parameter degrees of freedom will be taken off. So what is left will be three parameters. And three parameters because the body can rotate in 3 different ways. This is extremely important to understand, that the body, yes, can rotate in 3 different ways, which is, of course, rotations along the global axis. So it's rotation along x-axis like this, rotation along y-axis like this, and rotation along z-axis like this. I don't know if I think I made a mistake, but anyway, so you know that there's 3 different ways that the body can rotate. And that's important to understand. And now, why is that we want to make our life miserable and use 4 parameters instead of obvious selection of 3 parameters? Well, we wanted to do that because whatever you're using 3 parameters, you're going to face some kind of mathematical difficulties. The difficulty may be the fact that the rotations are not differentiable. So you can't differentiate what rotation is what. Or you may have another kind of difficulty in your rotation matrix. So it meaning that some of the components within your 3x3 rotation matrix, you cannot compute it. So it could be like infinite divided by infinite. So you just cannot get the values off. This is always a problem if you're using 3 parameters, and you cannot avoid it. At least there is no technology today that can avoid it. Maybe you are the person that can figure this problem, and maybe eventually you could be the one that is developing the method based on 3 parameters that is not suffering from any kind of mathematical drawbacks. By the way, if able to do that, that will be a big deal. But at the moment, we don't have it. And because we don't have it, we need to use 4 parameters. And again, the reason for 4 parameters is to get rid of the mathematical difficulties. Now, how is in this case of Rodriguez equation? Well, Rodriguez equation is based on the concept that you take your original vector and you attach a unit side vector v to your original vector. And then you're going to take a hold of your unit size vector v, and you're going to introduce the rotation that is amount of theta. And now, because of this concept, because of this procedure behind, you end up to have parameters that are associated to this unit vector v. And the unit vector v here is expressed in a way that the vector v is in a skew symmetric form, and that's what we discussed last week. So let me try to do my drawings here. So this is your vector v in skew symmetric form. And then 4th parameter that is used here is the angle theta. And that's it. No other parameters. And let me see, where is my mouse here? Here's my mouse. Now, this is a mother of all parameters, all methods that are using the 4 parameters. And now the very often used method that you can find in a commercial software is the one that these notations of v and theta are called from different name. And the name that they're usually called is based on Euler parameters. So you're using brand names, or you're using just you're using renaming technique, put it in a short. And you're calling these components that are used in Rodriguez equation by using these 4 names. So it's theta 0, theta 1, theta 2, theta 3. All right. And what these thetas are standing for, this equation shows to you. Now, once you have this naming ready, then you substitute the naming to your Rodriguez equation, and your 3x3 rotation matrix look like this. Very often used technique. Problem again, like always when you're using 4 parameters, is the usability is next to nothing. So it's almost non-existing because human brains are not trained to deal with the 4 parameters. That's a major disadvantage. But that's okay because many of the commercial software, they're using 3 parameters in a user interface, in a pre-processing and post-processing. And the computation itself is conducted by using 4 parameters. Okay, like that. Now, what we also discussed last week was 4x4 transformation matrix method. This is used in robotics to describe the robot kinematics. Let me just check one more thing here when I'm switching my slide, like how well it goes to you. It's not completely clear. So final tuning that I'm doing is okay, so this must do it. Okay, hopefully it's clear enough. So now 4x4 transformation matrix representation is method where you take your kinematic description used in a multibody system dynamics, which is this one here. So this is the vector that describes the translation of body reference coordinate system with respect to reference coordinate system. And then you have this 3x3 rotation matrix, which you can create by any means you want. And what you do in a 4x4 matrix representation is that you simply relocating these components to be in a 4x4 matrix. Goes such the way that the transformation matrix, rotation matrix, goes in upper left corner. So it occupies the first 3 rows and corresponding columns. And then the final column here will be the transformation of this guy. This vector R will be simply relocated to new location. And what is left is just a one more row, which you will fill by zeros and ones, which will be in a diagonal component, and it's called scaling component, which we don't want to do any scaling. So we wanted to make sure that bodies are not getting bigger or smaller because of the rigid body translation. So that's why the value is set to be 0. And now the beauty of this is that it simultaneously accounts the translation and rotation. And when you use that, it becomes to be easy to build the kinematic equation needed in a robotics. And there's special tailor-made methods that are using these techniques, which I'm going to introduce slide after this. Okay, now it goes like this. It goes like shown in this figure. So you can travel from one coordinate system to another with help of 4x4 transformation matrix. And again, like mentioned earlier, it accounts the translation and rotation, which is making quite a bit of sense because in a robotics, you wanted to account the robot bodies and the ways the neighboring bodies can move relative with respect to each other by using one single representation. And that's going to be that 4x4 representation. Okay, so like we discussed last week, so you can get started here in a coordinate U, and you can travel to this final destination, which is a coordinate D, 2 different ways. So you can travel here to here, and then here to here. So that requires 2 4x4 transformation matrices. Or alternatively, you can travel it by using B and C coordinate systems, and then you need 3 4x4 coordinate systems. So that's how it goes. So it helps to build the kinematics. And it really becomes easy when you're using some tailor-made technique like Denavik-Hartenberg technique. Idea in a Denavik-Hartenberg technique is that it accounts only several different ways that the bodies can move with respect to each other. That's the core content of it. Now, the Denavik-Hartenberg is based on 4 parameters, so 4 different ways that the bodies can translate with respect to each other. So the first parameter is this alpha parameter, which is describing how joints are possibly twisted with respect to each other. Then the second parameter is like a revolute joint parameter that is associated to this, hold on, it's this descriptor here. This one here, this is the one that is describing this twisting. And then we have parameter that is describing how much there is a rotation between the bodies. And, excuse me, I made an incorrect statement. So we account in the length of the body. This is the first figure. The length of the body, which is this description, and the twisting, which is this description. And we could have also this, how much they are traveled, like this direction. It is accounted here. And then how much is a rotation in translation revolute joint. Okay, so once you take these 4 parameters simultaneously into account, this is how the 4x4 matrix representation look like. Okay, now, is it good? Is it make your life easier? Well, it's good. It's good because the way this is intended to be used is such that you're building the table, that tables are such that these rows are corresponding bodies, and then these columns are corresponding 4 parameters in your dynamic height and back representation. Once you have this table ready, then you build 4x4 transformation matrix corresponding each one of these rows. So this time you're just gonna build the 3 4x4 matrix representation. And by the way, this describing this kind of robotic system here. And once you're multiplying them together, you know how is a robot kinematic. So you know where the end here is located as a function of joint parameters, joint space. And that's it. So it's kind of handy, but for sure it needs some training to be able to use this table. But we leave it for that. So we leave it for your information this time. So I don't expect you to be a master of this method, but just something that is good to you to be aware of. And good you to be aware of in a sense that it's all based on the same kinematic space that we are used to deal in the multibody system dynamics. Okay, so let's move on. Now, here comes that honestly a little bit of painful part of the lecture, which is telling what is the deal with this 3-dimensional multibody system dynamics, and just still doing some minor checking here to see if you guys are still on. I see I have 32 viewers, which is okay, and it looks okay. Great. Hopefully my internet connection stays stable today. All right. So as promised, so we're going to take a look at how this 3-dimensional multibody dynamics is different than 2-dimensional multibody dynamics. So let's make it happen then. Let's jump to the business, and soon you will see that, okay, this is how it is different. Okay, so the kind of the close the case about the kinematics is that we need to describe not just the position of the particle, which by the way is not complicated at all, but we also need to describe the velocity and acceleration. And those guys are then complicated. And the complication comes in the fact that we're kind of losing explicit expression of our generalized rotational parameters. And so 2 steps that we need to do: velocity and acceleration. So we need to describe first velocity, and once we have velocity, then we need acceleration. Okay, so let's get started from the velocity. So of course, we're going to use this equation that we are very much familiar with, and we're going to differentiate that with respect to time. Okay, well, the vector u bar, when we are dealing with rigid bodies, will be equal to 0, so we can easily neglect that component. So what is left is 2 components, like in a case of planar multibody dynamics. So we have a translational velocity, and then we have something that there is a dot, which is going to give us an angular velocity. All right. So I'm not going to explain in details how it goes. Hopefully this is there's a lecture notes available for you soon, which says that, okay, you can describe this A dot, which is a rotation matrix differentiated with respect to time, such the way that is skew-symmetric form of angular velocity multiplied by rotation matrix. Or alternatively, you can express it in a way that there is a rotation matrix multiplied by skew-symmetric form of angular velocity that is expressed with respect to local coordinate axis. Either way, it's still, you can pretty much select what you want. Maybe what we can do, make sure you understand the difference here. This is angular velocity with respect to global coordinate axis. global x, y, and z. This is angular velocity with respect to local coordinate axis, x, y, and z, small x and y and z. So, but you know, the idea is still more or less the same. Now, let's select that we're going to use this definition here. So this definition that gives us the global expression. All right. So let's substitute this information here, and this is what we're going to get as velocity. Here comes that difficulty. The difficulty is the fact that now we have here angular velocity, this one here. Angular velocity is not same than rotational parameters. So when you're taking a time difference, when you're differentiating angular parameters once with respect to time. So let's say that we have here vector that is angular parameters, and let's say that we're using Euler angles. This is theta, like this. When you differentiate that with respect to time, so these will be all dots. Now this guy here is not the same than angular velocity. How come it is not the same? Well, there is no way yet developed. I mean, I guess it is mathematically impossible to develop a method that these parameters are one-to-one same. You just cannot find that space. So it's not just possible to do it. So that's in short, the difficulty that comes in a three-dimensional multibody dynamics. But let's see how the story continues. And soon I'm going to have an in-class quiz. So be prepared, because this is what I'm going to ask over and over again. Well, not over and over again, but this time just that you get an idea. All right, here it is what I just mentioned to you. So there's no way that angular velocity and time derivative of rotational parameters are the same. There's no known way. I mean, that no one has developed the way that this is equal. So this is no way to do it. So what we need to do then is that we have to relate these two things together. And how is that we can relate these two things together will be with help of the mapping matrix that is called T matrix. And how you can do that in details. I have this story, put it in a writing in the lecture note, so you could take a look at that. But basically, it comes when you're employing kind of like a concept of virtual work. Is very complicated story, and maybe I'm unable to express that in short. But we do need this T matrix. Okay, T is something that maps generalized coordinates and angular velocity. Very important. And it's also very important because of the very simple practical reason. Because this guy here, what we are using in a computation, that could be, there's several different choices how this could be expressed. It could be these Euler angles, it can be Euler parameters, and many, many other ways. Now, expressing inertia properties in terms of Euler parameters, which are 4 parameters, will be a great challenge because, first of all, we have a lack of knowledge how are they behaving, so human brains are not trained to deal with that. So now how you can express mass moment of inertia and mass product of inertia with respect to something that you don't even understand what the heck they are, that's going to be very, very difficult. It's so much more easier to express mass moment of inertia and mass product of inertia with respect to something that is making more sense, which is, of course, with respect to local coordinate system. And now when we have this T here, this is the one that is mapping the representation to any rotational parameters you want. Okay, I know that this is painful stuff. Let's see if I can summarize this somehow nicely, because I know you guys are suffering big time, but still I'm going to ask a question related to this matter. And it's going to be after there's one more slide, and then I'm asking something about the T matrix in my in-class quiz. Okay. So how is this T matrix? For Euler angles, of course, first of all, the important observation is that it depends what is your rotational parameters. But if you're using Euler angles, the G matrix look like this. And now let's take a look. Let's make an observation about how is this G matrix. The first column here, when you look at that, well, that's obviously the z coordinate axis. Now, the second one here, if this component here is equal to 0, will be x-axis. And if theta is also 0, this is then z-axis. So it's telling you that how the rotations are taking place. And now if you don't use this rotation sequence, then of course you need to make sure that you're modifying your G matrix correspondingly. All right. So that's going to be my saving component, my saving angel almost, G matrix. And G matrix can be used in a way that it is mapping these guys to local angular velocities or global angular velocities. So either one you wanted to use it. Okay, let's take a look. G matrix is important because it couples local and global coordinates, because it couples angular, velocity vector, and time derivatives of generalized coordinates. It describes the inertial properties of a body, couples global and generalized coordinates. And I want to leave it here. So I don't want to give you any more repetition or any more, explanation, because I would like to see if there's something you got from this. Something. I know not easy, but let's set the challenge. Let's set the challenge. So I'm not yet in Socrates, so just a second. I'm gonna launch the squeeze. So it's on. Oh, come on, what the heck happened? No, it's okay, it's okay. So I can see that, yeah, I got the first answer. So at least there is something going on at your end. 3 answers, okay, 6 answers. So his answers are, or the number of answers are growing rapidly. And the game is on. Yeah, I'm kind of with that individual student that is guessing that the success rate is low. So I'm a little bit towards, say, less than a 50%. Less than a 50%. I'm thinking that, my guess is this. Let me type it for you. So it's going to be this one, 48. That is my guess. All right, there's, some of you are saying that it's quite high, like 80, 90, 98, which is a high, 96, 95. Yeah, 75, 72, excuse me. 72 would make sense, I think. 85. All right, we'll see. We'll see. We'll see in a second. And now another difficulty in my new settings here is the fact that, I guess that I'm unable to change the, let me see, I need to go to my OBS. Maybe I can add another window here. Display capture. What they said? What was the thing that I used? Window capture. Window capture. Okay. This one. Let's put it a little bit of like here, and then I need to put myself in a front. Okay. Windows capture 2. All right, oh, it looks okay. So let me see. I have 26 students. Let me look at my streaming window here, wherever that might be located at. Here. I see that I have 32 viewers, so maybe I'm expecting what I would say. Maybe some of them are not willing to answer this question this time. So let me see. Oh yeah, this is by the way quite cool because I can switch. I can take it off and put it back. I never realized that there is this option too available in OBS. But so 27 students. So I'm gonna close in a minute, and then we're gonna take a look. Now let me see if there is any comments. No other comments. Then the game is on. By the way, we don't have that many winners yet, so we'll see. And yep, that's about it. All right, so I'm gonna close in 10 and in 5, in 5, in 5, 4, 3, 2, 1. Okay, let's see. Oh, I cannot do it here, so I need to do it here. Well, this is good. Now, this is really, really good news. This is unbelievably good news. Look at this. So we got the success rate that is 82. 82 is it's getting excited, even though that there is this technical difficulties and everything today. This is really nice. This is great. 82. So going back to here, this guy. So there is some comments. Okay, so let me first check. Like, do we have a winner? We do. So we do. We have a winner here. Let me put the nice. Yeah, congratulations for winner. Do we have another winners? No, we don't. But we got the no. We got two. We got two. Look at the scroll up to the chat window. There is a. Let me see. There is a fourth answer was correct answer as well. So that's nice. So we got two winners. So let me just type down the winners. But I'm not going to mention the names, even though that there is a temptation, because it's and we need to be careful not to release the names of our students. So sorry about that. Now, what this is doing, what the G is doing for us, it is coupling the angular velocity and time derivatives of generalized coordinates. And this is kind of handy thing because, like I mentioned, it helps us to describe inertial properties because we can use any generalized coordinates associated with the rotation we want. And still we can use conventional ways to describe the inertia tensor. And the inertia tensor is all about how is a mass, product of inertia and mass, moment of inertia. Those are the things that are needed in a inertia tensor. And now we can express those using global coordinate axis. And then with help of G matrix, we can map them to any parameters we're using in a computation. So that's where it comes handy. Okay, so now what I will do here is, and I'm going to speed up a little bit. So because, this is become to be a little bit of nasty story. So it's going to be this G over and over again, and we're going to use the G in different ways. But the bottom line of the story is this. So when you differentiate it, when you're expressing your velocity, the only way you can express it explicitly in terms of generalized coordinates will be with help of matrix G. And matrix G depends on what kind of parameters you're using in this component. So that's it. That's the end of the story. That's much I would like you to be aware of. Nothing else. Okay. All right. So then when story continues, so we can express the acceleration, and the acceleration is more or less same that in the case of planar case. Of course, the dimension will be different. And again, if you wanted to express this explicitly in terms of generalized coordinates, it's going to be a big mess. But if you just differentiate the previous equation once more with respect to time, this is how it reads. So you got the three components. So you get the translational acceleration, normal acceleration due to the rotation, and tangential acceleration due to the rotation. And that's about it. That's what you need to know. Now, couple more painful slides and then we are done with this business. Now, if you wanted to express acceleration in terms of generalized coordinates, in terms of generalized rotational parameters, you can do that again with help of matrix T, and it's going to be a big mess that look like this. Okay, don't look at the details. Don't make the details to make you confused, because of course everything will be computed by using symbolic math tools, so it's not big deal at all. So the only thing that I would like you to recognize is that this conversion matrix that is converting your expression to generalized coordinates is involved here. So that's pretty much all you need to know. Okay, and now if we wanted to express all the component needed in equation of motion, the most painful one will be the inertia or generalized inertia forces. And generalized inertia forces, like we learned already last year, fall semester, you can get that by using a concept of virtual work. But not this time, we are not going to look at this in details. We simply say that inertia forces is mass multiplied by acceleration. And when we wanted to express that in a very sophisticated way, we wanted to say, okay, the mass is not the mass, but it's all the particles are counted within the boundaries of the body, such that the density is integrated over the boundary of the body. Well, of course, mass is equal than this operation. And then this guy here, we're going to express that by explicitly in terms of generalized coordinates. So be aware, that's what's going to happen next, and it's going to be looking bad. So this is our delta R, which can be expressed partial R, partial Q. Remember, this is this magical mapping matrix that is converting or relating global coordinates and generalized coordinates. This is what we need here. And now we can express generalized inertial forces as it is shown down here. So that's almost there. Finally, this substitution is, excuse me, not this one. This substitution is needed. So this velocity, and this substitution is needed as well. Hold on. Look at that. I can mute myself. So just to lift this mic and I can mute it myself. So I'm learning many things today. Okay. So here it is. This is the final big chaotic stuff. So I'm gonna substitute this magical mapping that is relating global and generalized coordinates and my expression of acceleration. And this is how it finally gonna look like. But don't look, because I don't want you to be confused. What is left is this one here. Now this is gonna be my mass matrix in three-dimensional space and my quadratic velocity vector in three-dimensional space for one body, for one single body. Okay, what is that I have here? And I have here identity matrix, which is 3 by 3 identity matrix. Then I have this component that do not have a clear physical interpretation. It's the one that is related in translation and rotation. And then I have here in the middle, very much in the middle, I have here inertia tensor, which is then multiplied by matrix T. And this is what I just mentioned to you. So this is your inertia tensor, which you can map to any configuration you want. Now mass matrix could have a dimension 6 by 6 or 7 by 7, depending what is the generalized coordinates, rotational coordinates you're using. So it's depending on the G matrix. If you're using 3 rotational parameters, it's 6 by 6. If 4 is 7 by 7. That's it. All right. So I don't want to torture you more about three-dimensional multibody dynamics. And let me see if I kept my promise. I didn't keep my promise. I said that 20 minutes. I don't know how long I spent. More than the 20 minutes. Finally, torturing is off. And we start looking more pleasant matters. And so breathe deeply. You made it. Congratulations. Now, from this on, we're gonna look about methods how the flexibility can be accounted. How is that we can describe deformable bodies? We will get started from the landmass approach, which you are already familiar with, and focus later on the floating frame of reference formulation. Floating frame of reference formulation. The first challenge is this. So if you know where the name floating frame of reference formulation is coming from, and let me emphasize what is the difficult here. Floating, what that is standing for. That's going to be already a great accomplishment. And I will explain that a little bit later, maybe even today, but that will be repeated a number of times. So what the floating is standing here. But we will get started from general introduction, and then landmass approach, and then finally we're moving on to floating frame reference formulation. And in that, we're going to look at how is a finite element modeling. You may be already familiar with that, but I can see from my YouTube studio that that my picture was frozen. I hope you can still hear my voice. It says the connection is excellent, but it's not updating streaming stop. Yeah, but that's what I was thinking as well. So is it back? Come on. So you said that is okay, but because for me it's not looking good. So I follow this streaming as well. Oh, you hear my voice, but the picture is frozen, completely frozen. Annoying business. Let's wait a couple. No, it's still not good. Still not good. So what is going on here? So should I stop the streaming and put it back on, or what would be the best way to go? Honestly, I'm not sure. Oh, you guys. Oh, all right. Let me do the same. So let me refresh it. And it's looking good again. All right. So it was all about. I don't know what was it. Never mind. Okay. So let's get started from the introduction. So let's first make a list of few important general matters that is good to know before we jumping into how to model flexible bodies. Well, first of all, first obvious question in general discussion is that why you want to model flexible bodies? Well, the answer for that is not simple, but generally speaking, you wanted to introduce deformable bodies to your model because you want to increase the accuracy of your model. And the accuracy, when you make an assumption of rigid bodies, may be okay in many practical applications. But then there are applications which the assumption is not okay at all. So you're making a very serious modeling mistakes when you're assuming all your bodies to be rigid. Because in real life, like we discussed earlier, there's no such thing like rigid bodies. every single body in this planet and other planets too are deformable bodies. Other planets, I'm not sure about that, but at least in this planet, they are deformable bodies. And is the deformation significant enough that it's making an effect or contribution to dynamic response? Well, that's hard to say. Sometimes it is, sometimes it's not. The reason to model the deformable bodies is that the deformation is significant. So you do the modeling of flexible bodies to get the better accuracy, better match to reality. Well, then the next obvious question is that how you know when it is necessary to model body as a deformable body and when it is enough to model body as a rigid body. There is no clear rule of thumb for this question. It depends on your application. They've been sometimes some introduction that if the force is introduced to your structure is very close to one of your natural frequencies, then it's important to model the structure as a flexible structure. But that's not necessarily needed in all practical cases. It's heavily case dependent, and there is no rule of thumb to say when body needs to be described as a deformable body and when it is okay to model body as a rigid body. It's all about your engineering sense. Like thinking about, do you think this it's important to take a deformation into account? And it's just about your call. So there's no rule, no equation that can tell if you can model your body as a rigid body or should it be flexible body. So that's a little bit unfortunate, but you can develop the method by yourself. You can look at how slender is a structure, this kind of thing. But even slender structures not necessarily need to be modeled as a flexible bodies. No rules, no instructions, general instructions available. So that's a first thing that is good to know. Okay, so let me ask you this. When a body deformation needs to be accounted in a multibody applications, when large force is applied to system, when a natural frequency of the body is low, when a slender, thin structure is in consideration, there is no general rule to make this decision. And let me put my Socrative on. Hold on, so it's how come my next here? All right, so go ahead. Oh yeah, I see that I kind of supposed to have 42 students in a system, which I doubt. I don't think that's the case, but I got 5 answers already, so it's up and running. Okay, and the game is on, so make your guess. Let me see, streaming here. All right, so game is on. First answer, first lottery is 82, 84. Okay, my personal is this. Look at that. 96. 96. That's a lot. 96. 88, 87, 94. Did I miss something? 89 was 1. 82 was 1. Oh, there is somebody close to me. 95. 81. 85. Okay, so let me see how is that. Let me see if this new feature that I just figured out in OBS, how well it works. All right, so here it is. So we got already 26 answers, and last time I think it was 27. I guess so. No, we got 27. So I'm gonna close it. So just need to find the proper window somewhere here. Oh, we got 28 answers. 29. How come? So some of you joined a bit late, I guess. Okay, so let's take a look. Nice, nice. 90, 90, it's good. It's good. Like, yeah, there's no general rule to make this call. This wasn't easy because, usually this kind of option is never a correct answer, but, this time it was. So, congratulations. You did really well. You did really well. Okay, so let's continue. Let me see what time it is. So we still have plenty of time left. Okay. So before we really jumping a topic is, I would like to explain something that is important. That what is important is that what kind of deformation we're looking at, because there's a own discipline within the multibody system dynamics, which is called flexible multibody dynamics. Now, this flexible multibody dynamics goes to two different schools or two different categories. The first category is the one that there is a people and methods that are capable to deal with small deformation, small deformations. Small deformations means that your strain displacement relationship is assumed to be linear. Okay, so what it means for us? Well, what it means for us is that if we have this kind of cantilever beam here, and you're loading the free end of the cantilever beam, what's going to happen due to this force is that there's going to be a displacement. Why? And the displacement will be along the length of the element. The x will be measured this direction. Now, how is the relation between the u, displacement, and strain? Displacement and strain. And if this displacement is linear displacement, then you are dealing with the small deformations only. And most of the cases, it's okay to deal with the small deformations only. This comes with a limitation, and the limitation becomes to be clear if we look. What's going to happen to this cantilever beam when we're loading that a little bit? When we're loading it a little bit like this, this is describing that situation. It's important to notice that the free end of the cantilever beam is remaining in the loading line. So if the loading line is here, this is where the original free end of the cantilever beam was. It's going to be in the same line after deformation. It still look okay, so it's not looking too bad. But if you keep on increasing the force, then you see that eventually started to look unrealistic. Because if the deformation is something like this, you don't see this happen in real life. Because in real life, the deformation would be something like this. The difference between the real life and the one that is here is that there is a little bit of displacement in axial direction. This you can only take into account when you have this strain displacement relationship to be nonlinear. That's what accounts that. This is in finite element literature and many other literature is called as a geometrical nonlinearity. It is meaning that the strain displacement relationship is assumed to be nonlinear. Well, here we assume that to be linear. When we're looking at the method, this floating frame reference formulation, it's all the time linear relation. And it comes with several different advantages, such like the one that now you can use a model reduction when you're assuming this relation to be linear. Then there's, of course, one more step to take. Of course, there's a relation between strain and stresses. This is stress here. So you know that there is always this curves, which there is a strain and stress. And for steel material, they usually behaving in a linear manner under the certain yield point. And after the yield point, there is plastic deformation. Now, in a multibody system dynamics, we typically are limiting us to this linear region. We typically not taking this plastic deformation into account. Plastic deformation means that if you keep on loading your structure, you hit to this point, and if you continue from this point, your strains is getting bigger, you will introduce permanent deformation in your structure. It means that when you take your loading off, the structure will not come back to its original deformation, original configuration, but there will be some permanent deformation in the structure. When you think about them, when you can see that in the real life in machines, you don't see that in the real life, because it would mean that you have a crane and you lift something with your crane and the arm of the crane is bended because of the lifting. That's not good design. So you don't see this relation. But keep this in your mind. Try to understand the difference. Displacement, strain, stresses. So what those are standing for. Okay, here's a simple example. So let's see if this is willing to play. Now I have two cantilever beams, and in the free end of the cantilever beam there is a pendulum. And the one that is closer to me, you can see that there's a nonlinear strain displacement relationship, because look how the free end of the cantilever beam is moving. So it's moving around the circular path. And because it's moving around the circular path, it will introduce some motion to this pendulum. Here is moving along the line. And because it's moving along the line, pendulum is not introduced. I mean, the pendulum motion is going to be no motion, standing still all the time. So these are the two differences. So now let's move on then. Lump mass approach. And let me check if there's any comments, any questions. By the way, there's going to be, of course, team sessions right after right after this lecture. And one thing that I forgot to do was that I did not collect the wieners from the previous case. Now I suddenly got the weird moving. So let me see if I got any wieners. I got. So I'm going to accept 83 as a wiener. 87 as a wiener. 88 as a wiener. Okay, I need to take a screenshot. Yeah, of course, my new computer is making all kind of funny things to me. So hold on. Just collecting the wieners and then we will go. Oh, this is much better way to collect the wieners, by the way. Copy paste. Copy paste. Okay, so I'm done with that. Now, so we're here. So we're going to spend 5 minutes to explain to you again this lump mass approach. 5 minutes only because it's not very often used. There's only one thing that is important in this lump mass approach, and it's something that is that we can learn a little bit about the computational efficiency when we're looking at this method. Okay, so method itself is extremely simple, very straightforward. And it goes such the way that you take your original body, typically beam-like body. It could be in very extreme cases to apply to plate-like bodies as well. But typically we are looking at the beam-like body, and you divide your beam-like body to several rigid bodies. And what you're going to do between these rigid bodies is that you will introduce spring elements between the bodies. And these spring elements will have a stiffness to all 6 degrees of freedom in the spatial case. And it means that you can use the same theory that in a rigid multibody dynamics, because there is no flexibilities involved here. Basically, where the difference comes is that can you use this kinematic notation? And yes, you can when you're using this approach. When we're going to use a floating frame reference formulation, we cannot, because this component will be added by amount of deformation. This is going to be showing where the original point is located at and how much it's going to deform. But, this is a method where you don't need this kinematic description, so it's using the same theory that in rigid multibody dynamics. And it's based on the neighboring body. So it even can describe nonlinear strain displacement relationship in a certain limitation. Because if you build a cantilever beam using this structure, and you're loading the free end of the cantilever beam, yes, you can recognize that there's a little bit of displacement in axial direction. This method, however, is suffering from very serious drawback. The serious drawback is the fact that whenever you're using this method, you will end up to have numerically stiff method. And now wake up, because numerically stiff is something that I'm about to ask in my next in-class quiz. So wake up. Numerically stiff. What is numerically stiff? Numerically stiff means that you are solving the system that consists of small natural frequencies and large natural frequencies numerically. So it's, if you make a line of how are the natural frequencies in your structure, you will have a certain amount of natural frequencies that are, this is 0 here, that are very, very small, and a certain amount of natural frequencies that are very high. Where you can find a system like that? Well, this beam structure is a good example, because the beam structure can have a bending deformation like shown here. Frequency associated to bending deformation is typically very low. So let's say that it's like 25 hertz, like this. Maybe there's another bending mode as well like this, so it may be 55 hertz, which are considered as a low frequencies. But then there's a very high frequencies, which are related to axial deformation between, say, this body and this body. So when they're moving away from each other in axial direction, there's a very high frequency that is associated to that. That could be, say, 5,000 hertz. 5,000 hertz. So now you have low frequencies and high frequencies. What is the problem here? The problem is the fact that when you are solving the response, let's say that the free end of this cantilever beam look like this. There's no surprises. But if you look at if you make a magnification about this point of the curve, you can see that there is this high frequency due to the high natural frequency. And numerical integrators are capable to detect that. They realize that, oh, wait a minute, there is something going on here. So there's something going on here. So let me look at that with care. So they tuning the parameters and they time step such the way that they are integrating this vibration here with high accuracy. But is it important? No, it's not really important for us, but it's killing the numerical efficiency. So that's why the good modeling practice is to try to avoid the cases that there is a large and small natural frequencies. Because even though that there are integrators that are tailor-made for this kind of problems, it is hard to use it. Okay, so here are the few examples where this kind of landmass approach is used, or maybe I should make this a bit bigger so it's become to be more visible. So it's used in a cable modeling, early models of cables. Now today there is a better models for cables, but let me see if it is running. Yep, now it's running. But this crane here, when you look at the cable, the wire rope here, the wire rope is modeled by using this landmass approach. And you can see that there is even a taut string effect. The taut string effect is that when you are introducing some pre-stress to your cable, its transverse vibration is affected because of that. Guitar strings are a good example about this taut string effect. So when you're tuning the guitar string, you're basically affecting the natural frequency of the string. And that's what you can see also in the cranes. A little bit of different concept, but still you can see in the cranes as well. Okay, so it can be used in this kind of wire rope models, but it's been used in many other kind of applications in the past. Not frequently used anymore, and not frequently used because, again, this computational complexity, this numerical stiffness that easily comes along with the landmass approach. Okay, so let's leave this. And here are the advantages, disadvantages. Computationally expensive, not efficient, but expensive, because numerically stiff system. What follows is in-class quiz where I'm asking what is a numerically stiff. Again, system with the low frequencies and high frequencies. Okay. Another disadvantage is that it can be applied mainly for beam-like bodies. Material damping is simple, easy to implement, easy to use, simple theory. I don't know if it's really great advantage, but still. Okay, here's my 13 class quiz for the day. And I'm asking what the numerically stiff means. That the system contains low and high frequencies, that the system contains high frequencies, that all bodies are assumed to be rigid, that some of the bodies are assumed to be flexible. And you're good to go. And I will build this one back. Let me see. Now there's so many windows here, so I need to see where this is the game on already, or yep, now his game is on. Okay, so let me see. I wanted to put my OBS, this one here. Okay, so I need to left. Nah, now it should be okay. Looks okay. So let me see. I'm curious to see what is that you guys are saying about the success rate. Yep, there's 100%. I'm with you. I'm also thinking it's 100%. My guess is this 100%. Because if you've been following my story here, this is easy. But I know that it's difficult because there's so many other interesting things going on in the internet. So maybe there's a high temptation to check out like another YouTube channels, perhaps something else, and you're losing your concentration and then you are not capable to answer this correctly. We'll see. I got 24 students, 24 answers, not students, and so I'm soon unable to close this. 99, 99. Okay. Let me see. Now I was frozen to that 24. So am I gonna get more answers to this in class quiz? I guess not. 24. All right. Still want to explain to you something about the floating frame reference formula. So that's why I'm gonna close this in 5. Well, there's a delay, so this makes no sense to do this countdown. Okay. Please place your answer, and then we will go. Let me see what's going on in my here. Okay, so the next one, okay, 29 students. I think this is it. So we are not gonna get more answers. So success rate is 90. Very good. It's good. I'm happy. I'm very happy. So this is, I don't think it can be much higher than that. Now, next or last 5 minutes, I'm going to spend with the floating frame reference formulation, which is extremely nice story because it's wrap up everything you know so far. Is about vibrations, it's about finite element modeling, so many things that will come together when we are explaining this, or when I'm explaining the floating frame reference formulation. Okay, so let's get started then. So a few observations. Now, the idea here, really the core concept in the floating frame reference formulation is that you're describing your deformation with respect the body reference coordinate system. And like the title floating implies here, the body reference formula from body reference coordinate system is kind of traveling with the body, kind of rotating with the body, but not rigidly. It is traveling in a floating manner. And this is like, what? So is it or is it not? And answer is yes, both. So it is traveling, but not rigidly. And this is something that is a little bit of mind-blowing. Like, seriously? How you can do it? We'll explain that to you next week. But it is traveling with a floating manner. So not completely rigid, but close to it. How come? That I will explain you a bit later. Now, the deformation is described with respect to this reference coordinate system by using the finite element modeling. And the finite element modeling, so basically the idea is that you have this potato-shaped body. You modeling the potato-shaped body using finite element discretization. You can use plate elements like shown here. Once you're done with your plate elements, then you're going to have your reference coordinate system somewhere. Let's place it, my reference coordinate system to be here. This is a reference coordinate system. So the deformation then will be described with respect to this reference coordinate system. And the reference coordinate system will be the one that is accounting the large translations and large rotations. So it's like kind of in a summary, this coordinate behavior is described by using multibody system dynamics. Deformation with respect to this coordinate system is described by using finite element modeling. Okay. Now, the obvious problem you can see already here is that, okay, these two things are not getting along well. You mean multibody and a finite element. And they don't get along well because, in a finite element modeling, you can easily have huge number of degrees of freedom. You can end up to have 100,000 degrees of freedom, 1 million degrees of freedom. And then that is described with respect to, this reference coordinate system, which needs 6 coordinates. Not good. They don't match. So we need to do something for that finite element model. And something that we can do for that is model reduction. That's where we need to look at this vibration, and we need to identify the properties of this finite element model. And these properties, we can figure it out by conducting an eigenvalue analysis. And eigenvalues tells us the natural frequencies and corresponding deformation modes. Those modes will be later used in conjunction with the reference coordinate system. And I know that how this sounds to you is like this. It's okay, because we're going to look this several times together. So it's going to be core content of the course, and we're going to spend some time to make sure that you understand this back and forth. Kinematics is changed. It's not going to be the same anymore, because now we're going to have point here, particle, and the particle is having original location, and then we're going to have a deformation which shows how much this particle is moving with respect to this coordinate system as a function of time. This is what we are describing using the finite element modeling. This is going to be the nodal degrees of freedom in our finite element modeling. That's what it is. And this is kind of like summarizing the situation. So we have reference coordinate motion, this guy here, which is described by using multibody system dynamics. And then we have the deformation, vector U-bar here, which is described by using finite element modeling. And because the finite element models initially are typically way too big to be used in a time integration scheme, we're going to reduce their size. And that's going to happen with help of model reduction. And again, idea in a model reduction is that we're looking at the features of the structure, and we're picking up those features that we believe are the most important ones and ignoring rest. It's a like magic thing that happens. We will lose a certain amount of accuracy, but not much. Not much. Because what it means to have 100,000 degrees of freedom, it means that the structure can deform in 100,000 different ways. Okay, how many of those ways are actually significant in the practical cases? Not necessarily that many. Maybe it's only 10 different ways that the deformation is significant. The rest is playing the minor role. And that's exactly what we're going to use when we're introducing this modal reduction technique. Here's an example. It's like how is the floating frame reference formulation used. These are the very preliminary tests that we have made sometimes 100 years back in LUT University. Here the connection rod is modeled as a flexible body. And here is simple beam, which is the animation is not so great. Like telescope arm that is modeled using the floating frame reference formulation. Now with that, I know that it's I wanted to get started with the description of deformation, which is essentially finite element. And I want to give you a little bit of insight about what is a finite element modeling. And that's going to be next week. But shortly, already this time, I would like you to know that, typically the finite element method is explained in a way that there's a nodal degrees of freedom. And that's all about the finite element method. Something that is between these nodal degrees of freedom is like black box, something that is insignificant. And finite element method is completely opposite. It's all about what do you believe that is between these nodal locations and how you estimating the behavior between these nodal locations. So it's all about that. This behavior can be described in many different ways. We're going to look at how you can use polynomials to describe this behavior between the nodes. And those will give you the inherent features of the finite elements, which is then extremely important. So that's why my explanation is a little different that you're used to deal with. But with that, I can see that it's getting late and we need to have this team session. Sorry about the big mess. But I knew this. I kind of knew that it's going to be hard today because my computer was in a service. I knew that doing all the settings correctly will be a major headache. Sorry about this. Next week, Wednesday, is going to be pleasant, more pleasant. I can guarantee you that. So let me close the recording and let me close the streaming and see you in a bit in a team session. I'm going to relocate the calendar invitation so you can get an alarm that it will be on momentarily. Okay, so let me just a final check for comments, if I have any. No, I don't. All right, so see you soon in Teams.